me, as you heard. And while you pull up your presentation, then after Filippo, it will be Hida Voss from TU Delft, and I think that's when we can safely go into the break. And after the break is then still this final session where everything comes together in the auditorium.
Yes. Thanks, Roland, for that. So today my talk is about a vortex model of the Airborne energy system aerodynamic way that we developed. And this is a bit the outline of the presentation. We start with some background that led us to investigate this topic, and then move on to the modeling. So how actually we can model the helicoidal trail vorticity, and then how we can model the near wave, the far wave, and then how we can actually refine the power equation, the log power equation, to take this into account, and and maybe some consideration on power coefficients with a novel power coefficient definition. Here, the two references related to this. So I will not really go through the math because there is a lot of math involved, but just to get you the main ideas. So from optimal control, we realized that we would like to have a really tight trajectory. Why that? Because those tight trajectories reduce the potential energy exchange over a loop. And by reducing the potential energy exchange, and we realized that this potential energy exchange somehow is detrimental for power production, because we need to decide if to convert it to electrical energy or if to convert that to kinetic energy. And this somehow conversion is brings some inefficiencies. And then from a design point of view, we would like to have a tight trajectory. But tight trajectory also increase induced velocities from an aerodynamic point of view. So we need somehow to have a trade-off between different disciplines in the design, and we need also to model this. So how can we actually model those induced velocities? I'm listing here three methods. One is momentum methods, one is like Vortex and CFD. I'm already ruling out CFD because on those kind of simple models we cannot really use it because it's expensive, of course, but also we cannot really draw some first-order conclusions from CFD. So we need some kind of analytical model. I'm the analytical model guy. And we cannot really neither use momentum methods, because momentum methods assume uniform distributed loads over the annulus in our case, and we would need the deeper root correction for the airborne energy system that is just one wing flying around. So then everything is a root correction, then it doesn't really work. So we need to use vortex methods. And we see here in the figure that we will model indeed the trail vorticity, which has an helicoidal shape for circular trajectory. And we'll see that how to model that. So we have this trail vorticity, and first we consider just one vortex filament, which has this shape, and we can then write Biot-Savart law to actually find the induced velocity due to this trail vorticity. And so we can parameterize this vortex system and somehow populate the Biot-Savart. Not go to the math here, but just for you to understand, and then we need to solve this integral. And how actually can we solve this integral? We need to do some assumptions, probably like some hypotheses. So the assumption we do is actually to split the integration interval. We can think like that, and neglect some terms that are like bringing us from the trail vorticity system on the left to the one on the right. So we model the helicoidal shape as a alpha vortex ring, which is the first integral. We see it here in the equation, which is modeling basically alpha ring plus an infinite summation of integrals modeling the far wake. So this infinite cascade of vortex ring. And so here we can identify a near wake and a far wake. And then we will start then to use this idealization actually then to study indeed the near wake and the far wake and see how they actually influence an induced velocity on the lifting line. So we start with the near wake. The near wake is this half rotational, half vortex ring in the rotor plane. We can think about that. And then we can somehow study it. I think, again, there is some math, I'm just showing the results. And we can plot somehow the induced velocities due to the near wake. And here we show we have some induced velocities that the same wing would have in forward flight and those velocities are constant over the wing. And those are the purple line. If then we model this half vortex ring, we have the induced velocities a bit with a slope. So there are different cases showing, but those are representative actually of the half vortex ring. And we actually realized that somehow, if we think about integrated loads, they're equivalent. And indeed, that's what math is telling us. So, and we know that we would like from the induced velocity to get to an induced drag coefficient. How do we do that? We go from the induced velocity to induced change in angle of attack, and from the induced change in angle of attack, we go to induced drag coefficient. And luckily, we found that it's the same drag coefficient, induced drag coefficient of the same wing in forward flight. That's great results, because that means that all the engineering models that we used more or less up to now that considered these as induced velocities was not, wrong, but was just considered the near wave. So we were kind of neglecting these infinite cascades of vortex ring. So we need a model for the far wave. And then here, of course, we need to take some assumptions again. So we assume that the far wave, the vortex sheet has already rolled up. So we have just one vortex for the right wing and one for the left. And then we need to look for a fitted solution to the infinite summation of vortex ring, because it doesn't have a closed form solution. But the same conceptually as before. So we have this infinite cascade. We find the induced velocity due to the far wave, and we get to the induced drag coefficient due to the far wave. And let's take a look how this expression is. We have, you see, the first is 1 over 4 pi, which is a constant. Then we have the near wake drag coefficient appearing in the equation. So it means that the far wake drag coefficient is also a function of the near wake drag coefficient. And then those two terms appear. So the inverse turning ratio, which is the ratio between the wing half, the wingspan half, divided by R0, which is actually the dependence we wanted to have in this model, saying, okay, if we fly really tight trajectories, then we need to see that in the aerodynamic model. And here there is the dependence for this. And the second term that appears there is this normalized torsional parameter, which is telling us how the pitch of the helix is. So it's basically like if it's large, then we have really tight loops of the helix. If it's getting small, then it's a long helix. But that's unknown. So we need to find a model to close this quantity with the rest of the quantities of the model. We can go a bit further, and we can also derive a glide ratio for the system. We know that the glide ratio is one of the most important parameters for airborne energy systems. And now we will take it as the ratio between CL over CD. In this case, also I'm writing the thrust coefficient of the onboard wind turbines is present. Like this model is valid for both ground gen and flight gen. You just need to plug the right number in. But now the drag coefficient is modeled with CD0, which is the viscous drag of the kite plus the tether drag, and then the two induced drag coefficients for the near and for the far wake. And then we see again here that the glide ratio now is functional of this turning radius somehow, and we start to have this dependence. So now we need to find this closure for the normalized torsional parameter lambda 0, and we get to this closure by taking some assumptions. That's how we proceed with engineering models, and we assume that the thread vorticities goes down with the velocity in modulus at the wing center. So we need to take in account both axial and radial induction at the lifting line. So now with this we can get to a solution, which will not be an explicit solution, but we need just to basically solve the equation down in the Ballet box, knowing the radial and the axial induction and the glide ratio as we see it there. Okay, then that's a bit, there is quite some math involved, but also we perform an extensive validation with tube blade to make sure that actually we were modeling the right physics, and for most of the cases it is indeed going the right direction. So, and this was the first part of the presentation in which I briefly introduced the reasons and a bit the direction we took in the development of this aerodynamic model. So the second is like, okay, can we actually include this aerodynamic model in the power equation of somehow the log power equations? We'll just show here the flight gen, but in the papers you find also for the ground gen, just for the sake of brevity we do this. So now, like log power equation usually is like derived based on given CL and CD. Here we don't have anymore the assumption of given CD, but we just assume a CD0, like viscous drag plus stator drag, aspect ratio, in this case also gamma, so how much we load the onboard wind turbines, K0, so the turning radius, okay, basically, like this non-dimensional parameter, and in this case also this CT telling us how big the onboard wind turbines are. So then we can derive the onboard wind turbine thrust equation, then from that onboard wind turbine thrust power, the shaft power, taking account the onboard wind turbine induction, and we need to remember that we also need to consider the wake, okay? So we need to impose the equation for the wake to be fulfilled. In this way, we have a refinement somehow. We take, we model the actual, like, infinite wake behind the Airborne energy system into account in the derivation. Okay, so then a question we can make ourselves. It would be nice also to have like somehow a power coefficient as we have it for conventional wind. And that was a question that a bit triggered my thoughts on here. So like, what is then a good reference area we should take? What is the most meaningful reference area we should take? So in literature, the two that are reported are the first two somehow. The first is related to the disks swept by the AWESs during the generation. I don't really like that. Why I don't like? Because it's function of the turning radius, and the turning radius change with wind speed. At certain wind speeds, we will have a given turning radius, at others another turning radius. So it's a bit, yeah, could be representative of something, but usually we like to take somehow CP, which is fixed with the geometry of the system and not with the way we operate it. The second is the wing area. Okay, so the wing area of the lifting body somehow, and that's leading to the power harvesting factor. Even here, like we don't really do that for conventional wind. We don't take the blade area as the reference area because the area is more representative of the loading and not really on the dimensions. In conventional wind, if you think about that, like then we take this reference area, which is the disk, which is actually function of the blade length, and that's the blade length is the one actually defining the reference area. So maybe we could do something similar for us and take a reference area which is functional just of the wingspan, okay? And that's the reference area I'm proposing here. So it's a disk with radius equal to the wingspan. And by the way, it's also the same reference area of wind turbine with the same lifting body span somehow. And so we use this reference area. And we get to a CP, okay? We take the equation in the slide before, we normalize it, and we get to this CP. And what is actually this CP? Let's briefly look at some results in terms of this CP. So we can, for a flight gen, write this simple optimization problem in which we optimize gamma, so how much we load the onboard wind turbines. And but yeah, we need to take into account that we need to fulfill the equation for the far wake, okay? So we impose this far wake equation. And then we start to see the CP here. We see it for a few values, and we see that this CP is on the order of 1, can exceed the Bert's limit and 1 because of this definition of the reference area. And we also see that higher aspect ratio are optimal at higher design lift coefficient. So if we design our system with a lift coefficient of 2, then we see that the higher aspect ratio are optimal. So a question we can come out is like, okay, but given a wingspan, and so given this reference wing area, this reference area, what is the aspect ratio that maximizes power? This could be like a design question somehow, right? And we can approach this with a numerical approach, saying, okay, we have the same basic optimization problem as before, which now we have also as a design variable the aspect ratio. And we can approach the same problem also analytically, somehow. We take, we neglect the far wake, we take some assumptions, and we solve this problem by taking the derivative, the partial derivative of this CP with respect to the aspect ratio, and then we look at the solution for when it's equal to 0, so then we look at the maximum. Then we find this simple equation telling us what is the optimal aspect ratio that maximizes DCP. And conceptually, this is like, okay, we fixed the wingspan, and then you say, okay, what is the optimal aspect ratio that maximizes power? Of course, if you have a really high aspect ratio, then we don't have an area, basically, so we don't generate power. If we have a too small aspect ratio, then we have too much area, we drag a lot, there are too much induced velocities. And we find this expression here, in which we see that the optimal aspect ratio is function of CL squared, which conceptually is like the design lift coefficient, so the coefficient, the lift coefficient we designed for. And CD0, which is, I recall, is the viscous drag coefficient plus the tether drag coefficient, okay? And in this plot here on top, we see the analytical approximation is the dotted line, okay? And the solution of the numerical approach, with the numerical approach are the red lines. And we see that somehow they are like in the same, the analytical approximation approximate well the numerical results. And the numerical results are obtained with an increasing K0. K0, I recall it is written there, is the ratio between the wingspan and the turning radius, basically. So, yeah, for increasing K0, then we decrease the turning radius, okay. And then also we can say, what if we use this aspect ratio to get to the maximum CP? And again, we can solve it with the two approach. And the maximum CP, we find that it's really neat solution. So it's CL over CD0 over 27. And again, we see it here, like with on the plot on the bottom, in which we have the analytical solution and plus the solution, yeah, including also the far wake, basically, including this turning radius. Okay, then there are some conclusions. We derived this vortex-based aerodynamic model, and then we have an induced drag coefficient for the near wake and one for the far wake. And we should include them both, like it's easy to include them. And we just need to fulfill one equation. So let's start to consider also this in our models. Also, it's validated with Q-blade, but it would be nice to have all the sort of other, I mean, also comparison with other fidelities and so on, and see maybe we can refine this. Maybe there are some assumptions that in some cases it doesn't hold, like and so on. And then we refine this power equation by including the wake, and we propose this new power coefficient definition using as a reference area a disk with radius equal to the wingspan. And we found that the optimal aspect ratio is finite. We have an analytical approximation for that, and also a maximum theoretical power. And, yeah, thanks for the attention.